So welcome to this presentation. We're going to spend the next 90 minutes talking a little bit about graphs, in particular graph databases. My name is Emil Eifrem, and I'm the co-founder and CEO of Neo4j. And I have with me on stage here Michael Hunger, who leads up the Spring Data Neo4j project. And we have a super simple agenda for today. But first off, I want to set the ground rules for this talk, because I have very specific and strict ground rules for all of my talks, and they're the same. They are, I do not want your undivided attention. We're all online. The Wi-Fi here works sometimes, occasionally. It's occasionally consistent, right? So if you have feedback, if you have any questions, feel free to either raise your hand and just ask them ad hoc, or tweet about it. The only thing that I do ask is that you use the Neo4j hashtag, and in particular, I want you to also tag it with S2GX, because we're going to have a little fun with that later on. So the agenda is really, really simple for today. We're going to talk a little bit about connected data, graph databases in Neo4j. We're going to zoom out a little bit and talk about why I think graph databases are particularly relevant today. And then we're going to dive into Spring Data Neo4j. We're going to talk about a sample application, wrap up, and then there's Q&A. And I think if we get to a point where there's a big Q&A session at the end and everyone has been quiet up until that point, I see that as a failure. Please do interrupt if I don't make sense, or for some reason if Michael doesn't make sense. I'm sure he's going to be more coherent than I will. Then do raise your hand and interrupt, and we'll take it from there. If there's a question that requires a bit more thoughtful answer, maybe we'll push it to the end. So I'm going to start by telling you three really, really quick stories. And they're related to connected data, just to spoil the stories immediately. And the first one is about the evolution of web search. If you guys recall, I'm not sure how long you've been around, but there was an internet before Google. Yeah, believe it or not. How many in here remembers Alta Vista? Hands up. Wow, most of you. Awesome. How many remember Excite? How many remember Razor? Yeah. It was actually an Alta Vista skin that made it look like Google. If you recall, Alta Vista was super bloated with like all these kinds of gadgets and widgets, and they were a portal. But then Google came around and they actually launched a skin called Razor with just one text bullet. Anyways, back in those days, all search engines pretty much worked the same. They downloaded the entirety of the internet, the entirety of the web, at least that was their ambition, onto some data center, or probably several data centers, and then they crawled it and built up a huge index in order to find what's available on the web. Then in 1999, something magical happened, right? Larry and Sergey came around and they said that, hey, I will download the entire web, and I will look into every document in order to find what's going on. But not only that, I'm also going to look at the connectivity of the link graph, as they called it, i.e., I'm going to use, if one web page links to another, as sort of a voting mechanism, right? And if multiple web pages links to one web page, that's multiple votes. And then when you guys search, I'm going to use that to rank the search results. So they started inventing this algorithm called PageRank, right? And what ended up happening here is that pretty much every other search engine on the planet went out of business. This industry, this particular industry, had like in a moment, it came to a tipping point where if you didn't exploit the connectedness of data in this industry, you went out of business. More recently, actually the same week as Facebook did their IPO, Google launched their next initiative, which is the single biggest upgrade to the single most important algorithm on the web since PageRank. And they call it the knowledge graph. And it's basically, actually, we'll go into the details of that later on. If we then look a little bit more abstract than at what we have here, we have a situation pre-99 where we worked with what I call atomic data, which is data about a single individual, the documents, and every content on that document. And then 99 came along and Google started exploiting simple connected data. And that completely changed this industry. And now, most recently, they started exploiting rich connected data with a knowledge graph, which is basically not saying that, well, we've managed to exploit the links between pages, but now we want to exploit more. We want more types of relationships. We want to go from a single relational graph to a multi-relational graph. And now they store things like, hey, this web page is about an actor. This actor acts in several movies. So when you search on that, you're going to get a bunch more search results and more validity into that. So that's one industry, my first story. The second story is about online job search. There are a bunch of companies in this age. If we go back to the Alta Vista age, there's like Yahoo and Dice and all those guys. But more recently, there are companies like Bright.com and Resonate. And Bright has a really cool feature where they look at your CV, and if you give them your CV and a specific job posting, they're going to say that, hey, looking at your CV and looking at this job posting, I'm going to give you a score of 4 or 7 or 9. And higher score means more likely to get that job, which is kind of cool, right? But what happened just more recently is that a bunch of these kind of companies called Glassdoor, etc., started exploiting connectedness. And all of a sudden, we had a social element. So all of a sudden, there's a company now that rather than just looking at the individual CV, they're going to look at other people with similar CVs to yours that have applied to similar positions as the one that you're applying for, and use that as the basis to predict whether you're going to get that job or not. What's happening right now in online job search is that if you're not exploiting connected data, very soon you're going to be out of business. So that's the second story. The third story is in the progress right now. I'm less convinced about this one. We're sort of reaching a tipping point. We have some advanced knowledge here. But let's see how this plays out in the past couple of years. It's web browsing. Pre-2012, every major web browser on the planet was using atomic data. You click on a web page, you go to that web page, and that's it. And now there are 2 projects. I can only talk about one of them publicly, but 2 of the main alternative web browsers that aren't owned by a big corporation, are now looking into exploiting connected data to build the next generation of web browsing. The one that I can talk about is Mozilla Pancake, which is Mozilla's browser in the cloud, which is incidentally completely based on Neo4j, a graph database, where they start using graph databases or graphs and connected data to take the next generation of web browsing. This industry seems to be in the tipping point. If these 2 are successful, either these 4 old big guys will have to move to exploit connected data or go out of business. Question? Can I elaborate more? The question was, can I elaborate more on that? Yes, I can, and I'll be happy to do that after this session. So we talked a little bit about these 3 industries, right? And we have a couple of other markets in evolution right now. A year ago, I was here at Spring 1, and when we looked at NoSQL as a landscape and zoomed in and specifically looked at graph databases, we saw this as the main market and fertile grounds for where graph databases seem to be adopted. We have software companies, we have finance and insurance companies, we have communications companies across a number of use cases. And what's happened since then is that we've seen an explosion of graph database uptake across verticals and across use cases, completely horizontally available right now. These are all Neo4j customers particularly. Remember, I'm a vendor, so I represent Neo4j, so you should take everything with a huge grain of salt. But the point here is that all of these industries are now at a tipping point where they used to be able to just exploit atomic data. Now they need to move to connected data or go out of business. So the question then is, what is connected data? Well, another word for connected data is graphs, and at this point everyone seems to be talking about graphs. Facebook's API is called the Open Graph API. Google again launched their knowledge graph. Even Oracle wrote a blog post a month ago where they said that due to the increasing demand of graph database technologies, we're renaming what used to be called Oracle Spatial and Graph. Oracle Spatial and Network into Oracle Spatial and Graph. So even big Oracle is now moving into graph databases. So what then is a graph database? Well, if you have a lot of connected data and you want to store that connected data, it may make sense to you that you want to use a relational database because relational databases, as you know, supposedly are good at relations, right? I mean, you can hear that. It's in the name. So let's look a little bit at how that works in a relational database. Let's assume that we have a couple of tables. We have some food tables and we have some bar tables. Sorry about that. And we want to link them together. So we have foo items, we have bar items. If we want to connect foo items with bar items, what do we do in a relational database? Well, we put together a join table. We call this one foo bar, right?
Sorry.
And then
I just realized that my power will not last for the whole session. But remove the
we practiced this beforehand, just to keep the suspension up. So we have, no? So we have this foo bar join table, which joins elements from the foo table with the bar table. And wait for it, foo bar, and the foo bar, right? So if we have an element over here in the foo, of the foo type, we want to link it to elements in the bar type, we join using key value pairs in a join table, right? But it turns out that if you look at that in the way you would instantiate it, let's say in Java, most of us here use the JVM, I suppose, you know, since we're Spring or Groovy people. And it looks something like this, right? We have a bunch of objects, we connect them using relationships, and these relationships are what's basically represented in the join table. Like this. So then the question is, what if we in memory have a representation like the one over there, and we conceptually think of it that way? Why don't we have a database that can natively work in this way? And of course, the answer to that is that we do, and it's called a graph database. Specifically, what we're talking about here is the property graph model. So a graph database like Neo4j works with a data model called the property graphs, which has three fundamental abstractions. It has nodes, it has typed relationships between nodes. Typed relationships. This is important. The fact that I work with Michael is different from I am a friend with Michael. Now, both can be true at the same time, but they're not necessarily the same. So the fact that, you know, there's a type between two nodes is very important. And then we have properties, key value pairs that we can attach to both nodes and to relationships. As a bonus, we have indexes because we also want to be able to find a starting point in the graph so that we can traverse. It turns out that when you work with a data structure like this, it becomes what we call whiteboard friendly. And whiteboard friendliness is the observation that we did when we first started out building consultancy projects with Neo4j. Back in those days, I'm not sure how you guys work with when you engage with new clients, but the way I work is that you get people, you know, you shut the doors to a room which is wallpapered with whiteboards, and then you talk with the domain experts and you brainstorm, you know, tell me about your world, tell me about the problem that you're solving, tell me all about that. And you end up drawing a bunch of things on whiteboards that, ironically enough, very seldomly is tables. Maybe if you're modeling like a payroll system where the data is inherently tabular, maybe the domain experts will draw tables. But unless they're plagued like I am with a computer science education, where I've been trained to go first normal form and third normal form and ER modeling, etc., very seldomly will people end up natively drawing tables on those whiteboards. And what we found over time was that if you model a domain, have a domain expert model a domain, it ends up very frequently as a graph. And what we found out as customers, when we built these systems was that 6 months down the line when we put it in production, we saw a one-to-one mapping between what was on those original whiteboards and what ended up in the graph, in production in the database, which is kind of interesting. And this tells me that the cognitive model of the domain expert is that of a graph. And the programmer, when he sits down and works with a graph database natively, not with a relational database, also has the cognitive model of a graph. And that's one-to-one reflected in code and in data, which ends up being very, very powerful. So that's all nice. That's what my esteemed colleague Jim Weber calls that's nice, but it's a little bit hippie bullshit because it's compile time advantages, it's soft advantages, right? So what about some real hardcore number advantages? What about performance? So a while back, we were contacted by one of the big social networks in the world, which shall go unnamed. And they said, we've looked at all this NoSQL, there's key value stores and there's document databases and yada, yada, yada. But we found graph databases and we think that's by far the most expressive and powerful model. That's the easiest way to represent our world. So we really like you guys. However, we're big social network X, and the only thing we really care about is performance. So they asked us, can you send us some benchmarks? And us being the honest geeks that we are, we said, hey, we can prove anything with benchmarks. So how about instead you give us a scenario that is relevant for you and we'll show you our numbers. And the scenario that they gave us was the following. Create a social graph with roughly 1,000 people, with exactly 1,000 people. Construct 50 average friends per person. So with 1,000 people, that's 25,000 total connections between those people. Grab 2 people at random and check if they're connected. Limit it to depth 4 because otherwise, Kevin Bacon, everyone is going to know everyone. So limit it to depth 4. Warm up caches because we want the overhead of the model not going to and from disk. And then look at the numbers for this. And we did that with a relational database, which shall also go unnamed in this scenario. With 1,000 people, that was a 2,000 millisecond performance. And let's reflect on that a little bit. 2,000 millisecond, that's enough so that you can't use it at runtime. If you're rendering a page like Facebook's newsfeed or LinkedIn's, first page, you can't have a 2,000 millisecond. You need to have probably 50 millisecond or 100 millisecond in order to render a web page at real time. And why is this? It turns out that this is what I like to call the sweet spot of suck for SQL, which is arbitrary path length relationships. When you grab these 2 people at random, you don't know ahead of time how many hops away they're going to be. If you know that, it's fairly easy to express it as a join in a relational database. But if it's unknown, it's a horrible, horrible thing. I think this one ends up with 32 joins. It was 5 pages of SQL code just to express this query. So anyways, we ran this in Neo4j, and no surprise, it's a lot faster, right? In fact, it's 1,000 times faster. So we were super happy about that. But we ended up not stopping there. We wanted to see, so how does it scale, right? So in Neo4j, we then added 1 million. This is on my XX laptop, so it's a while ago, with a 300 megabyte heap for the JVM. And with 1 million people, 25 million total relationships, we grabbed 2 people at random, checked if they're connected within depth 4, and it's still a 2 millisecond operation. With MySQL, oops, it took several weeks before that operation was completed. So when it comes to really complex connected data and these kind of queries, a graph database is vastly superior to a relational database, which, if we take a step back, is the entire promise of NoSQL, right? The era of the one-size-fits-all database is over. For 30 years now, our job as software engineers has been, choose a middle layer, choose a framework, choose this and that, and then choose a vendor of a relational database. That's been it, right? And that era is over now. Now our job is to look at the data we have, look at the shape of that data. If it's graphy, awesome. If it includes lots of connected data, let's use a graph database. If it includes lots of tall, skinny tables, like a bunch of key value pairs that are not connected, awesome, let's put that in a key value store. If it has a lot of relational tabular data, sweet, let's put that in a relational database. That's our job these days. And once you choose a data store that is specialized like that, for the type of data that you use, that's when you get these kinds of amazing performance advantages. Okay, so how do you query this graph then? Well, it turns out that there's a query language called Cypher. Michael is going to talk a lot more about that later. But it's a pretty interesting one. Let's imagine that we have a graph which includes people and tweets, and every tweet has a tag. And we want to find the person called Andreas, the user called Andreas, and then give all the tags from all the tweets that he has sent. In Cypher, you work with three main clauses. There's actually a couple more, but three main clauses. You have a start clause, you have a match clause, and a return clause. And Cypher, the query language, is basically a pattern matching query language. And the meat of Cypher is in this match clause, which is the second clause. I'm not sure if you can pick it apart, but the important thing to note about Cypher is that it's an ASCII art query language. So maybe you can see that if you look at, how would you draw a graph using ASCII art? Well, the nodes you might represent as, two parentheses, and the relationships as arrows, right? So over here we have a node that we call user, which is connected using a has sent relationship to a tweet, which is then connected using a tagged by relationship to tag. So if we start at Andreas, the red node down there, we're going to make one hop to the tweets, which is immediately connected to Andreas, and then another hop to the tags, which are all the blue nodes in this picture. Very simple way to express connected data query. And Cypher includes a lot more bells and whistles. For example, the query that we talked about before, arbitrary path length, you just describe as a little star. You add a star. Or you can add, hey, give me all the all the tweets. Give me all the nodes that are connected to Andreas via has sent relationships in either one hop away or two or three. Then you just do 1.3. So it's super simple to express fairly complex things that would take a lot of time to just describe using SQL. So that's the Cypher query language. Then really quickly, specifically about Neo4j as a graph database. Up until this point, I've talked just generally about graph databases before we dive into Spring Data Neo4j and how you use Neo4j from a Spring environment. We said that Neo4j is a graph database. That should come as no surprise at this point. Graph database consists of two words. There's graph and there's database. The graph part means that it uses a data model called the property graph. Remember, nodes, relationships, and properties. And the database part is important because we actually are a database in Neo4j. And a database, in my mind, is something where you can store stuff, you commit, and then later on you can get it back, which is not true of everything in this world that calls itself a database, because sometimes it loses that data between you store it and you get it back. That does not happen in Neo4j. We have chosen to be focused on ACID, at least as a starting point. ACID transactions, and I'm not sure if you all remember your database theory, but it's basically atomicity, consistency, isolation, and durability, which is what we would call normal transactions in a relational database. There's a lot of hype in the NoSQL space right now, or has been for the past 4 or 5 years, about eventual consistency, and the opposite of ACID, which is called BASE, which is sort of a contrived acronym, meaning basically available, soft state, eventually consistent system, which basically means that you loosen up this more strict consistency requirements. And we think that's great because the benefit of using eventually consistent systems is that you're going to be able to scale out to many machines. However, we think that you should do that starting with a really strong transactional foundation, because you can always relax consistency. That's very easy. Whereas if you start with an eventually consistent system and have to build strong transactionality into it, that's really difficult. So we ended up starting with ACID transactions. We scaled to many billions of nodes and relationships. We do between 1 to 2 million hops per second in a graph when it's cached in memory, so when the caches are warm, which of course is substantially faster than any other type of database, NoSQL or not. There's 2 deployment models. One may be particularly relevant to an audience like this because it can be embedded in the JVM. Fundamentally, it's a bunch of jar files. And you can embed it like any other library, like Lucene, for example. But like Lucene has Solr and Elasticsearch to make it available over the network, Neo4j also has a server model, which makes it available using a RESTful API. And then we have a high availability mode, which scales out Neo4j horizontally. So you can run it on 10 machines, and every machine will have a copy of your data set. And this is good for fault tolerance in case some of the machines falls over. And it's good for read scalability. We've already talked about this. And then finally, there's a bunch of customers using Neo4j in production right now. I just made a copy of this one out of the website. It refreshes, but these are some examples. A question?
So if you're ACID and you're scaling out and you're partitioning horizontally, which I seem to hear you say, how do you handle things like cap? I mean, how do you make sure that you have that strong consistency across multiple partitions?
So the question is, if we're ACID and we also scale out, so what about cap, the cap theorem, and how do we handle the strong consistency across multiple machines? And that's a great question. So in the HA mode, the scale out mode, the default is to use eventual consistency for reads. And strong consistency for writes. So if you write to a slave, there's always one master and potentially many slaves in an HA cluster. If you write to a slave, what the slave is going to do is that before it acknowledges that write, it's going to go over to the master, whichever is the master at the moment, write it to the master, apply it to the slave, and then return back. So that's strong consistency. It's going to be a copy at least in 2 places at that point. But after it has returned back to the user, it is then going to eventually, on an asynchronous, basically asynchronous thread, copy that over to the other slaves. So at that point, it's strong consistency on the write and looser consistency on the reads. Can you repeat that? I didn't catch the question. Yeah, in Neo4j. Yeah. Okay, you said in Neo4j. Yeah. So the question is it tweakable? How many of these copies that you're supposed to write to before it returns back to the user and says yes, it's now been written? And this is inspired by the Dynamo model, where you can tweak N, R, and W in order to get various forms of consistency on your operations? The answer is no. At this point, you cannot tweak that. It's hard-coded to 2 in case you write to the slave, but that's one of the things that will be available in upcoming releases. Another question over here? Yeah, so the question is, in horizontal partitioning, currently I've spoken only about replication, so every machine has an identical copy of the graph, modulo, of course, eventually updating operations. But what if you want to partition the graph? So parts of your graph is over here and other parts of your graph is over here. Today, that is not possible, but that is one of the key strategic projects we're working on right now. And we're going to launch that at some point next year. It turns out to be a non-trivial problem because a graph is a very connected data structure, and the enemy of horizontal scalability is connected data, right? And what other NoSQL databases have chosen to do is say, hey, let's just have a very simple model that can't model connected data, because that's how we can scale out horizontally, which I think is an excellent choice. We've said, well, dude, the world is connected, so we need to reflect that in the model, because otherwise our model can't model the world. If anyway you have connected data, then you're going to run into this problem regardless of which database you choose or not. So that's sort of have been why we chose to embrace this connectedness. But that does make the scale out a lot harder. And I'm not going to talk too much about it, but you can imagine how you want to identify clusters in the graph and say that these parts over here are not very connected to the parts over here. So let's put them on one machine and these guys on one machine, and things like that. Any other questions? We are just about at the handoff point to talk about Spring Data Neo4j. So if you have more questions, interrupt Michael, or we'll take it at the end. Right, final question.
So in databases, every table needs a primary key, right? So what represents a primary key in the graph?
Great question. So the question was, in a relational database, you need to have, or you're supposed to have a primary key in every table. And what is a primary key in a graph? So that's a great question. So I'm going to answer that in two ways. The first one is the real way, which is it depends on your domain. So if you have actors, then you're going to, on your domain level, say that this is a primary key for the actor, and then you should store that on the nodes that represent those actors. The same is true if you have people or insurance policies or whatever it may be. However, Neo4j also provides a unique node ID for every node. When you create the node, it is completely empty. It has nothing except one ID, which is a 64-bit integer, or a long in JVM speak. So that you can use that one. However, we recommend that you don't, because we actually recycle those IDs. So if we delete that node, at some point in the future, another node may appear with the same ID. So if you have exposed that externally as a primary key, that can get messy. So in that case, we encourage you to craft your own primary keys.
So if the idea of a primary key is not there, then how do you retrieve whatever you put in there?
Yeah, that's a good question. So the question is, so then how do you retrieve what you've put in there? Well, you work with indexes. And so there's an indexing concept which currently delegates to Lucene. So basically, Lucene, at a very high level, Lucene is going to solve the problem of, given that I have a username called ABC123, which node does that map to? Lucene is going to solve that problem for you, give you that node. After that, you're going to use the graph database capabilities to query. If you look at some of the code, yeah, probably even here, right? So here we start with the node tag by looking that up in an index. Find me the tag that represents S12GX, right? S12GX, Spring 1, 2G. Yeah, that's right. That tag, right? So that's one example of that. Awesome. Without further ado, Herr Hunger, please take the stage. Oh, that's right. Fine. I'll do that. So let me just give you the brief history of the Spring Data Neo4j project. So Spring Data Neo4j was actually started, is it 2 years ago now or 3 years ago now? Man, time flies. Which was just post the VMware acquisition of SpringSource. And I was working on Neo4j, and we saw that coming from a JVM background, we felt that we wanted to get closer to the JVM community, specifically to Spring, because we felt that Spring would be a good framework for us good community for us to work with. So actually, the first prototypes of Spring Data Neo4j was hacked by myself and Rod, of all people. Throughout 6 months, this was pre-Spring Data. So Spring Data didn't exist at the time, and Rod was very interested in these alternative databases. So we spent 6 months pair programming every other week or every third week or so, hacking up the initial prototypes. After a while, when we saw that, hey, this stuff looks really promising, we should be able to take what's fundamentally a fairly crude model from a programmatic perspective. If you look at the raw Java API of Neo4j, and I designed it, so no knock on it, but it's fairly crude if you're used to all the nice features that you get from working with a relational database in a framework like Spring. But we saw that we were able to take that and make it a lot nicer in Spring. After we've proven that, we thought, let's give it to some real programmers. So Rod and I then gave it to the Honorable Michael Hunger.
Thank you. Okay, thanks Emil for introducing it. Now we'll dive at least a bit into Spring Data Neo4j. I will touch some of the possibilities that you have, and there is much more, but it's too much to cover in these 45 minutes, so we'll see how far we get. And actually, it should advance, right? It doesn't. Right. Okay, another of these nice things.
Is this when I'm supposed to entertain the audience with my juggling?
Exactly. So I thought I copied your slides over, but it was obviously, we started the wrong presentation. Yeah, so of course you know Spring Data because you watched the keynote that marked it on Monday. So Spring Data is an initiative of VMware Spring Source to give Spring developers easy access to NoSQL technologies. And Spring Data Neo4j in particular is the integration library for Neo4j. And as Emil already said, we chose to support the simple programming model that you're already used to from GPA. So that means we use an annotation-based programming model where you annotate your entities, and that allows you to provide enough metadata to actually store them in the database. We don't want to dumb down your access to the NoSQL databases in Spring Data in general, and also not in Spring Data Neo4j. So it's always possible to drop down to lower level operations that are beyond the object graph mapping, and also to core operations of the Neo4j API, because after all, introducing indirections like an object graph mapper always costs performance. So if you don't need the niceness and convenience of the automatic mapping, but you need the ultimate performance, then it allows you to drop down to the core APIs. Spring Data Neo4j, as well as the other Spring Data projects, supports the repository abstraction that Mark and Oliver and others have already talked about. And we also provide two mapping modes. So the first mapping mode is a very simple one where you actually take the data out of the graph, store it in the object, and the object is completely detached from whatever's in the database. So it's like in GPA, when you end your transaction, you have a detached object, and whenever you access something that's potentially not there, then you will be greeted by one of these nice exceptions that you all know and love, I think. The second mapping mode is more powerful. It's in kind of transparent read and write through mode that we use AspectJ for, which actually maps your object properties and references directly to the concepts in the graph database, and allows for more powerful operations. But it's, for instance, not feasible to use with Neo4j server because you then have the network hop in between. And as I said, we can use Spring Data Neo4j also with Neo4j server as well. So imagine you have an entity that's connected to other entities, and so what Spring Data Neo4j gives you as first is to be able to store those, and not just to store the entities, but also their type in the database. So as Emil said, Neo4j itself is schema-free, so we had to implement a mechanism on top of that that keeps the type information in the graph, so when you just get a node from the graph database, you're still able to identify which type it originally came from. We also support some other features as well, and I will detail them some more. So this is one of the examples of Emil's old school entity model, which actually just stores a node in the entities, possibly in a superclass, of course. But actually, you pass in a node into an entity, and every getter and setter is just redirected to that underlying node. And you can easily imagine that for larger domains, larger domain objects, that was like lots of boilerplate code, right? Fortunately, now we employ Rickard Oberg, the author of Xdocklet. So if you would have to write such code, you would probably use something like a generator like Xdocklet to generate it, actually. So, but that's a lot of code that you actually don't want to see in your domain objects at all. That's why in Spring Data Neo4j, a domain object of the same complexity looks like that. So I just annotate the tag with node entity, provide a place for Spring Data Neo4j to actually store the internal node ID that Emil mentioned. And I just put a name field in there, and the library already knows that it can store the name just as property in the graph as well. And we can easily add other sensible meta information as well. So for instance, when we want to be able to look up this tag by its name, then we say that's an index property. And actually, I want it to be unique. So that kind of takes care of the uniqueness question of before. So if I annotate a class with @node entity, it will be represented as a node. The fields will be saved. References to other entities will be actually stored as relationships in the graph. And if you have actually properties that are not supported as primitive types in Neo4j or as storable types in Neo4j, they will be converted using the Spring conversion facilities. So you can also write your own converters that convert properties of a certain kind into a format that Neo4j understands. And you just instantiate the entity, fill it with data, and store it in the graph. That's it. Then there's also relationship entities, which might be unusual and interesting. As Emil said, we can store as many properties not only on nodes, but also on relationships. So that means relationships in a graph database are a first-level citizen in the data structure and actually in the database engine. That means we should also have support in an object graph mapping framework to support relationships as first-level entities. So if I have a domain model where the entity is actually so important that I want to represent them as entity in my object model as well, then I can do that by annotating it with relationship entity. And as a benefit, I would also have the ability to actually retrieve the start and end node of this property as entity from that one. And otherwise, it's handling properties as well. So this is an example of what I just spoke about. So we have what we've already seen, the node entity, the ID, an indexed property. And then it gets interesting. So we have the user entity, which is another domain object. And we don't even have to annotate it. But it will be actually stored in the graph as a relationship with the type of the field name here in this case. And other entities like tags, mentions of the tweet, and also the original tweet for retweets are also stored as related entities, so as relationships in the graph. And I can customize the relationship type, for instance, here. And something else that's important that you already kind of know from the JPA world is how far do I want to fetch data from my database. In the graph, it's especially interesting because if you just go for eager fetching, so it means I follow every relationship to an arbitrary depth, then I will easily end up with the whole graph in memory because it's richly connected. So as long as you just continue following relationships, you will just pull everything into memory. So we decided to go for a shallow default fetching, and you can annotate fields to be fetched eagerly if you need it in your use cases. The repository abstraction that we support is located in Spring Data Commons, so all Spring Data projects can benefit from that infrastructure. And as you've seen in other talks, certainly, you just actually define an interface and configure the namespace, and then you get out-of-the-box support for CRUD operations, index lookups, traversals, and many other ways of interacting with the graph database. How does this look like? So this is that's the whole configuration that you have to have in your either XML configuration, or you just use enable Neo4j repositories and on your Java-based Spring configuration. I should put that in. And then you can start writing domain-specific repositories. Means data access objects that allow you to represent domain-specific operations on your database. So it works by creating an interface that extends an interface that we provide, which is bound to a certain type. In this case, it's a tweet. And then you can start, actually, if you don't have any methods in this repository, you still get all the things I just mentioned over here. So all these operations out of the box. So you can call all these operations on the interface. But then you're also able to extend this repository interface by custom methods. So either by methods which will be similar to Rails and Rails finders, be parsed from the method name and the actual meta information that exists from the actual class. So if I look at the tweet class, we have a tweet ID here, we have tags here, and the tag, as we know, has a name. So if I look at these finder methods, this one will just look for the tweet ID property of the tweet, and this one will see that there's a tags field in the tweet which represents a relationship in the graph. And these tags have names. So actually it first validates that these finder method names can be parsed and matched to a property path kind of. And when that is successful, this check, it actually generates Cypher queries for those. So it generates something that looks a bit like the thing here, down here. So it would say, okay, I know that there's an ID property, a tweet ID property in tweet, and oh, by the way, I also know that's an indexed property. So that means I can just generate a Cypher query that does an index lookup, returns the tweet, and that's it. I can also say, okay, I have tags via a relationship, so I have a query that looks up the tag by its index. It follows the tagged relationship backwards to the tweets and returns actually the tweets. But you can easily see from here. And so this query is generated at startup time. It will fail on startup time if there's something wrong and not working. So you get kind of early feedback on if your queries are successful or not. In STS and IntelliJ also type completion for these finder methods via plugins, which is quite handy, and they also show you the red squiggly lines if it doesn't match any meta information it has. And the other way to do that is to annotate actually the methods with a query. In our case, it's Cypher query with placeholders for the parameters that you pass in. And then you can also decide to actually pass in page information and get pages back. So I forgot to add the page information here. And how are these repositories used? There's a mechanism in Spring Data Commons that scans your class path for these kinds of repositories, either tagged by an annotation or extending an interface and core interface from Spring Data Commons transitively. And all these interfaces will be collected. These finders will be resolved. All the other methods of the interfaces will be redirected to a core implementation. And so it provides all these repository instances as Spring Beans, which can be either injected or pulled from an application context. And then you can just use them wherever, in whichever service controller or batch job or wherever you want to use them. As any other Spring Data implementation, we also support the template pattern or abstraction. So you certainly know the JDBC template from Spring Core, which gives you kind of a convenient access to relational databases. It wraps exceptions, it does exception translation. It gives you a quite handy and convenient API to execute statements, pass in parameters, convert results, and so on. So we do the same here, and also in other Spring Data projects. What we added is, because we didn't like the kind of explosion of methods, I think there's 73 methods in JDBC template or so, and as we didn't like this explosion of methods, we rather opted for a result handling, small result handling DSL that allows you to take results in a more generic way and then convert it to any type and collection type and filter on those as well as you need and want. And the template also works, of course, with the server and so on. So that's kind of the basic building block of Spring Data Neo4j, and the whole object mapping infrastructure uses the Neo4j template under the hood to actually interface with Neo4j itself. And the server support is just by changing the definition of the graph database that you want to use, and it's just passing in a URL instead of a file system place where to find the database. That brings us to code. So ending the boring slides, or almost ending the boring slides, we go to code. So the app that Emil already mentioned, that is running all the time in the background, so I hope you tweet it, because then it will be part of the graph with S2GX. We use a bit of Spring Social, actually just the Twitter search, Twitter template and the search of that. And a very simple domain of tweets, users, and tags. We have some connected entities, repositories, a service, and we have both a standalone app with an embedded Neo4j, and right now it runs against the Neo4j server that runs on my machine. Emil already mentioned the whiteboard friendliness of Neo4j. So we can actually model our domain in two ways. One way is to kind of do it abstractly. We have tweets. Tweets were posted or sent by users. We have tweets mentioning other people down here, and tweets are tagged by tags. That's about it. If you want to see a concrete example of that, then I would see in a tweet is actually the tweet content. Users have Twitter handles, and text would be nothing like that. And we'll see that in a minute. So, but we don't have to see the thing here, but I would like to go to the actual implementation. Any questions so far? Yes, please.
When you add that index annotation, what does it name the index?
The name in the index is derived. Oh, sorry. The question was, what is the name in the index that's been chosen for the field? So the default is that for the index itself, it will resolve to the class name, to the short class name, and for the key that's inserted into index is the default the field name, and it's customizable to use something else.
If you were to specify the name, and you specify the same name for multiple entities?
The same index name, so they have the first level separation is on the index name, and the second level separation is on the key. So if you specify the same index name for multiple entities, it will, depending on the index, it will either allow it, because then you can actually use something like cross-entity search, or you, for certain other indexes, it doesn't allow it, and then it will fail. For other index types, it will fail. So it depends on the index itself. But it's easily customizable, so you can just specify field names, index types, and things like that. So you can see down here, it runs the query, and sometimes it has problems with the Wi-Fi here and can't import stuff, but most of the time it actually fetches tweets and followers and things like that. So so we start with something simple. That's the tag, which has just a simple property, which is its name, which can be passed into a constructor, and it doesn't have anything else. Just a simple node entity. Then we go to the tweet. Actually, we should go to the user next. The user has a bit more. It has the actually it doesn't have much more. It has just the Twitter handle as field. The interesting entity is actually the tweet itself, because it contains the tweet ID that we all know from the Twitter status URLs, the actual tweet text, 140 characters, and then you see here that we have the user without any annotation as field in here, but Spring Data Neo4j can still derive that user is a node entity, and if it's a node entity, then it will be represented as a relationship in the graph, and if you actually want to see if you actually want to specify or customize the relationship type and not just default to the name of the field, then you can do it with a @related_to annotation, which is also used for other things, like, for instance, specifying the direction. So if I had a relationship that would not point from the tweet somewhere else, but it would be incoming to the tweet, for instance, a relationship that other tweets point to this tweet, then I could specify something like direction incoming for this relationship. Which is very handy because in Neo4j, all relationships, despite them being directed, can be traversed in any direction. So either for outgoing or incoming. So it's not like in an object model where I only have one direction to follow references. I actually can follow relationships in Neo4j in both directions. And the fetch annotation, as I already said, is used to actually eagerly fetch the other things. So these here should probably not be there because that will cause, was probably just some demonstration that I put in there. Yeah, so how is all this used? So as I said, we have these repositories that we can use. Actually, let's start with the tag repository. So the tag repository is one of the very convenient repositories in Spring Data Neo4j or in Spring Data in general, which just don't have any methods on their own. They just inherit methods from their superclasses. So if I go to the superclass, then I see it's composed out of several repositories. And if I, for instance, look into the traversal repository, I find a method that will be then available as as part of the graph repository. And the core repository is actually the CRUD repository, which provides the usual suspects of saving, finding, counting, deleting entities, and finding all entities of a certain type. So all these methods will be automatically implemented by kind of using a base class in our library, and will be available on the tag repository. So if we go, for instance, to the Twitter service, and if I have so that's the service I use, and I just get these repositories injected from my Spring context. And if I would, for instance, try to use tag repository.save, then this would actually already work out of the box. So I don't have to write any code for these kind of typical boilerplate CRUD-like methods that I don't actually want to repeat time and again at every project that I write. This also kind of leads us to how are these repositories used. So what I actually do is I use, as I said, Spring Social. Yeah, I use Spring Social, so I just get the, where is it? Yeah, I just get the Twitter template, search operations, and I pass in the search string. In our case, it's the tag s2gx, which is passed in as a parameter. And I just get the search results, iterate over these search results. So of course, it's not so easy to find alternative domain class names for tweet, because they call it tweet, we call it tweet, so it's, you have to decide on which one you will actually fully qualify. And then these tweets will be imported, which actually is pretty straightforward. So I create a user with this username. I have the user repository save this user. And actually the uniqueness implementation in Neo4j will return the originally already existing user in the database if there was already one. And if there was no user so far, that will create one. It's a kind of get or create operation. Okay, so we have the user for the tweet, then we get the text and the tweet ID and the user. We construct a tweet out of that. Then we add dimensions and tags by just adding them to the relationships. And So I just add mentions and add tags as entities to these collections. And after I'm done with adding mentions, adding tags, and adding the, if it's there, the original retweeted tweet, if I have all the information in my tweet, then I just save it, and that's about it. And that's all the code I need to get stuff from Twitter, put it into my domain object, save it in a graph database, and make it available for more advanced queries. To look at some of the more advanced queries, we could look at the user repository, which actually has a method that says suggest friends. It's not used yet, but you could easily imagine I pass in a user, and I want to see which other users were mentioned by this user in his tweets, which he does not follow yet. Right? So he talks about those people, but he doesn't follow those people. So, and these could be suggested as new followers. So that's one use of a Cypher query that is more advanced and just annotated on a repository method.
Is it possible to use in where is it possible to use property of connection?
Yeah, of course. So in Cypher, if I have, like here, a connection, a relationship, I can assign it to a variable, for instance, posted. And then I can say, and posted time is greater than, and then for instance I could also pass in a parameter for the time, and then I could say, okay, I have something like that. Right, so I assign here the relationship to a variable name or identifier name, in the where I can use it and its properties to do something with it, and I can use parameters in the where clause as well, which are referring to the index position of the parameter here, or there's also the possibility to actually annotate this with param. Let's see. Param something like, I don't know, time, and then I would use time here. So that's also possible. Okay, and then we can actually look at the, let's see. Or did I not have the tweets here? So the server is running right now, the Neo4j server, in which the tweets are inserted, and so far since I started this, we have 200 tweets with S2GX in there, and we can use the data browser, for instance, to find one of the tags, which might be S2GX. So we find the tag, and then we can actually visualize that. And all right, there I had it in the open in the other browser. There we are. So that's the data browser for the server, and here's you see the tweets. They are tagged with a certain tag here. We see that many other tweets also hanging onto this tag, and we have actually people in here like Oliver, who follows other people, who send certain tweets, and which is also mentioned in other tweets. For instance, in this tweet here, that this one mentions Oliver, I think, or someone else. So, and here in this data browser, I can also start to go to Neo4j console, start querying, and experiment with that, explore my data, and derive interesting use cases for using this kind of data. And second example that I'd like to show is the, let's see, where are we? Yeah. It's the Hubway Data Challenge, which is similar to the Twitter example, but I started the wrong presentation again. Similar to the Twitter example, but actually, so this is, for instance, one of the more advanced queries that you could do with or tags appearing in tweets from the same user, but which kind of tackle different domains. In this example that I created for Mark for the keynote, you actually search for a tag that contains Obama and check if those people also tweeted about things which they tagged with Romney. So that's an example for doing that. And it shows something like regular expression support, aggregation, the count stars in aggregation, ordering and paging as well. So which is all possible with the query language. And which is already a four-way join or would be a four-way join in a relational database. Right, we saw that. Something else that was quite interesting is the Hubway data challenge. So those of you that are from Boston certainly know Hubway as a bike sharing, so similar to Zipcar. Hubway is a bike sharing network, and last Friday they decided to issue a challenge for visualizing the data. And so as it was just past midnight or so, I decided it would be nice to just use Spring Data Neo4j to import these CSV files. So it's 500,000 bike rides and about 100 stations that they provided. And so I thought it would be nice to import it using Spring Data Neo4j and visualize it with Cypher and D3, which is a very nice JavaScript visualization framework. And if you look at the domain, it's very similar to that. So we have bikes, we have people that rode those bikes, we have stations somewhere, which have also, interestingly, lots of names, so 3 names at least, and interestingly also geoinformation. So we can use that, for instance, with Neo4j Spatial to do bounding box queries or distance queries from a certain point for that. And so importing, using a CSV reader and importing the domain model is pretty similar to what we saw in the Twitter example. What we added on top of that was, courtesy our Chicago luminary Max DiMarci. He created the D3 visualization in Ruby using Ruby and JavaScript, and I converted it to using Spring MVC to run in this Java app. So what we actually have in the trip repository is a method that gives me the aggregate information, which stations were used most often, and orders the whole information by the usage actually, and then returns the whole thing as a trip count, which is kind of a virtual interface which kind of encapsulates or captures the query results in an object-like interface. So it's kind of simple mapping that I don't have to write any code for that, but it just maps it automatically. And then I have to do some munching to convert this data that's returned from Neo4j into the JSON format that D3 expects for rendering. But that shouldn't concern us. All that should concern us is actually the Hubway controller, which just does, I have a repository, I call the statistics method onto it. I pass in a page information, so I just want to see the top 200 stations. So the first page of the 200 stations, and I sort it actually by number of writes per station pair. And I get all the data back, and then I do the data munching and return the JSON string. And my GSP is just a tiny thing that does JavaScript loading, so it doesn't do anything. And the JavaScript is just D3 API, shouldn't concern us that much. But what we want to see is actually the the result, which looks like that. So it currently runs on the machine, and we have this nice visualization where we have these bands. So each of these segments is a station, and the width of the segment is the aggregated count of all writes from and to the station. And the width of the bands is also the number of writes to a certain other station. So if I highlight this one, and I see all the writes to these other stations as well. Which leads us to the finish line. So, any questions about the code, the annotations, what you can do with that? So there are many more things you can do, but it's kind of the intro. Yeah. Yeah. So the question is that I should explain what you can do with boundary queries. So Neo4j itself, as a graph database, is very well suited to store spatial data, because spatial data, after all, is just nodes connected to other nodes on the Earth coordinate system. And then on top of these kind of raw information, you put different layers. And all this information is handled by Neo4j, especially by implementing different geo APIs. And one of these APIs handles also just bounding box and distance queries. So if I want to use that, then I say I implement spatial repository, graph repository layers. From trip. So and then in the place, for instance, in the hub controller where I have the trip repository, I can say trip repository find all by range, and I can pass in. No, sorry, this was wrong. Find all. Doesn't show up. Question. Find within bounding box or find within distance, and I pass in latitude, longitude, and distance in kilometers, and then I can, for instance, use it like that. And there's also one with bounding box where I do the x, y, and width and height of the. So that just add the spatial repository, and then you have these spatial methods available, which uses Neo4j spatial under the hood to execute them. So, yeah.
I think I thought I found that project on GitHub, but it's a Ruby project. Was that one?
Right. So I put the Spring project on GitHub, but without the visualization. So I just recently. Oh, sorry. The question is this project on GitHub, right? So Max, who is our Chicago luminary, wrote the whole thing in Ruby. And I converted it to Java, but it's just on my local machine. I still have to push this visualization part. But the import part is already on GitHub. There's also a blog on neo4j.org that describes the data model and how it's actually done. A blog post on neo4j.org that describes the approach. So where are we? There we are. Yes? Yeah, so
like for example, some folks have used the impermanent database, and I'm just wondering how that works with like the repository and how you can get those things to behave.
Yeah.
If you're writing queries or you're using that and the requirements come in and they change, you don't want necessarily pull back too much data or change what the query is without having a test surrounding it that you know what you're expecting back.
Yeah. Yeah. So the question is how to go about unit testing Spring Data Neo4j, especially with the certain requirements that may come with the no schema-free operations. So in general, Spring Data Neo4j ties in quite nicely in the Spring testing infrastructure. So as Neo4j, as Emil said, is fully transactional. We also fully support the Spring transaction support, the declarative transaction support. So within Spring tests, If you use add transactional in a test, then it will, in the same way as it does with relational databases, it will roll back your changes to the database, so you don't have to clean up the database every time you run a test method. You can also use, as you mentioned, the impermanent, which is a memory-only testing graph database implementation of Neo4j, which just uses not a file system, but a in-memory file system to store the data, which is a bit faster. Not actually, interestingly, not so much faster, but it doesn't store anything on the file system, and which can just be configured by passing it into the Spring configuration for Spring Data Neo4j. Just some closing remarks. So we have books. So I have 2 books here. So people who ask questions may come here afterwards, and I have at least 2 to give away. And it's also available as free ebook on InfoQ. You can easily go to InfoQ, download it there, and it covers the thing, the library pretty nicely. Then, as Mark already said, we have the modern data access for Enterprise Java Spring Data book from O'Reilly, which you can all get for free from your attendee sheet with a code. And I can get started on pretty animation or not. On Neo4j.org, we have this on our booth. I also put some here developer cheat sheets for Spring Data Neo4j, which are quite handy because they cover all the configuration, annotations, some useful links, and so on on the front table here. Spring Data book, and of course it's easy to get Neo4j directly from our site as Neo4j server, or use just the Maven dependencies or whatever dependencies you want to, or on Heroku as well. And Neo4j Google group and Spring forums are the places to go for questions, discussions, feedback. So I'm looking forward to many of you trying it out and seeing lots of good feedback from there. Yes, please.
It seems that Neo4j is a pretty good fit for Java JCR repository.
Yeah. So the question was, is Neo4j in itself a good fit for GCR, Java Content Repository type implementations? Actually, there were some people who worked on implementing a GCR implementation on top of Neo4j for their individual project. I'm not fully aware how far they've gotten or how far they went with that, but it's pretty straightforward to implement a GCR on top of Neo4j. Not too much, so it's not kind of publicly, or it's something that's published and maintained, but it's people did it for their individual project, but kind of not as open source efforts also. And closing, we have, so if you happen to be in November, on the West Coast, so November 6th in San Francisco, close to QCon. So if you go to QCon anyway, then take the chance to get a 50% discount for Graph Connect, which is a one-day graph conference, which with lots of very interesting speakers and lots of hands-on workshops, coding. We have a community lounge there where we can interact with our people from the community very closely, and will be lots of fun. So make sure to be there when you're there. And I want to just close with any other questions that you might have. Yes?
Can you speak to the differences between the aspect J and the simple configuration, and why I would use one over the other?
Yeah, the question is the difference between the simple mapping and the aspect J-based, more advanced mapping. So the simple mapping is generally useful when you don't have a very complex domain model and just are interested in storing things in the graph and retrieving those individual objects without doing more advanced operations like navigating your object graph and at the same time want to navigate the Neo4j graph. The aspect J model is very powerful because it allows you to seamlessly integrate Neo4j with your object model. So every change to your object model will instantly be persisted in Neo4j. And it's also transaction aware, so every change you did within a transaction is only visible in that transaction. And if you roll it back, then it won't be there. And if you use some, for instance, Neo4j Core API or Cypher statements directly on the database, then your changes will be visible directly to those. And for the simple mapping, they will only be visible after you stored information. Yeah. So.
As far as the server mode versus the
Yeah, exactly. As I already. The question is, how does this relate to server and embedded mode? So the SPJ mapping really works only in the embedded mode, because that's kind of no network in between the server and the database and your application. There was another question?
Yes, actually, in the foreign language, do you support the Gremlin instead of the Cypher? And when it does, which one do you recommend in this case?
That's a good question. So Spring Data Neo4j also supports Gremlin as query method on the template and on repositories. And I think, I personally, as I also work on Cypher, and I really think the expressiveness of Cypher and power of Cypher leads to much more readable queries and easier to understand queries. I prefer to write Cypher queries because I always am not able to understand the Gremlin queries I wrote 2 days ago. So it's.
But how about performance? Is any?
Yeah. So. For performance-related questions, it actually depends. So for some cases, Gremlin is faster than Cypher. For other cases, they are on par. We're currently working on improving Cypher performance in 1.9, Neo4j 1.9. So right now, if you want to really have high performance interaction with the graph database and are not afraid of using a bit more complex API, you can use Gremlin, but then you can also use the Java API directly, which will give you another performance advantage, if it's really performance you care about. Yes?
So you told the great story about query performance, but what about write performance? What about ingest performance? Any comments on that? So for example, you had an annotation or something that said, oh, this needs to be unique. Well, that has, I assume, very stark performance implications. If when you're writing something, it needs to have unique ID.
Yeah, so that's true, of course. The question was, how does do different annotations, like for instance, uniqueness, impact write performance? So in general, transactionality and also uniqueness constraints, for instance, impact write performance. So there are also several modes of Neo4j how you can ingest data. So if you have to ingest lots of data, you can go with a non-transactional signal-threaded mode, which is non-contention, so it will insert much faster. And regarding uniqueness, it's more or less limited by the performance of the index provider, in this case Lucene. So how fast Lucene can actually retrieve data from the index limits your uniqueness insert performance. So we're working on allowing other index providers easily to be integrated, for instance, something like Redis, which would be probably much faster than Lucene in doing something like that. So that's something to look out for the next releases. Yes?
I've noticed in writing Cypher queries that where you start depends. Sometimes you can traverse faster than if you start in other places. Is there any plans to have, or can you currently see like an execution plan, almost like a query execution plan?
Yeah. Yeah. So the question was, for Cypher performance, right now it depends on how you write your query. That will all change in the near and far future. So we're working currently on Cypher performance improvements, also on something like execution plans, and also on more intelligent execution of the query. So we started to already reorder things internally and use more information about the graph internally to improve the performance. And that's an ongoing effort. So with every Neo4j release, there will be more Cypher performance until we are on par with the Java API. That's kind of the goal. Okay, I don't know. We have 3 more minutes, I think, right? Any more questions? Otherwise, yes, please. Yes. So the question was, how does delete refer to cascading, or how do I cascade deletes, for instance? That's a good question. So something we haven't spoken about, that Neo4j, despite its being schema-free, has one very strong integrity constraint. That is, relationships always have to have a start and end node. There are no dangling relationships. So we are not the World Wide Web where you can have 404s. That also means, for instance, if you want to delete a node, it must not have any relationships attached to it. That said, of course, many people ask about cascading deletes. Cascading deletes are an interesting feature because, especially in a graph database, if you do it wrong, you can easily end up deleting your whole graph because everything is connected. And providing a generic way of defining, for instance, cascading constraints, cascading depths, and so on, leads easily to writing a Turing-complete language, as you probably know from GPA, and it can get very hairy how to specify cascades and how they relate, for instance, to different use cases, if you don't have one general way of doing that. And let me quickly finish that. Actually, we wrote a language that allows you to specify cascading deletes. That language is called Cypher. Because Cypher Neo4j 1.8 also allows updates to the graph, so creates modification and deletes. So with Cypher, you can easily express the depth and the types of relationships that you want to follow when doing cascading deletes. And then when you collected all the nodes and relationships in your Cypher expression, you could filter them as well. Then you say, and now please delete all these relationships and all these nodes in one go, and they will all be deleted in one transaction. So Cypher is our answer for having a language to describe cascading updates and cascading deletes in this regard. Because otherwise we would end up with a second language that's doing exactly the same stuff as well.
Do you support batch operations like inserting billions of nodes, or it will be million transactions?
The question is if you support batch operation of inserting, for instance, millions of nodes. It depends. So we have a batch mode both for Neo4j, for Neo4j embedded, which does not run with transactions, the one I already mentioned for data ingestion. We have also for Neo4j server, there's also a batch operation that can handle. You can pass in several thousand requests in one go, which also will be executed in one transaction. And also to Cypher, you can pass in. For instance, when you ask Cypher to create nodes, you can pass in an array of data, an array of maps actually, and then all these nodes will be created in one go. So I can create, for instance, an array or a list with 50,000 or 100,000 nodes or so, and then create them all in one go in a single Cypher statement. So there are means for doing that. Yes? So could you repeat it louder?
Is there a notion of poolable connections?
Neo4j, so the question was, are there poolable connections to the Neo4j server? So the Neo4j server uses HTTP to interact with your application. So there's per se, right now, no connection semantics. We are currently thinking about improving or changing the Neo4j server or updating the Neo4j server APIs to also include something like cross-wire transaction and things like that. So that is also something to watch out for in the future. It's the maximum of connections to Neo4j server are currently just limited how you configure the server, how many actually threads per CPU it should spawn. So kind of the number of your CPUs and how many threads per CPU you want to have limits the maximum number of concurrent connections to Neo4j server.
Right, we're running out of time.
We're running out of time. Thank you a lot for your attendance and all your questions.
Both Michael and I will be around, so please stick around and ask your questions. And if nothing else, please download Neo4j and try it out.
Yeah, so check out.
Thanks, everyone.
Check out the cheat sheets and the stickers, and feel free to grab a book. There you go.
Thank you.